Well, welcome, champs, to our first Mr. B's Not Here video. And I'd like to start with a little quiz over naming. We've got a blue molecule here, pinky right here, a little red one, a nice purple one, go a little high, hunter green, and it's supposed to be brown, but it looks kind of orange. So first thing I want you to do is I want you to pause the video. I want you to dial into each one of these molecules, and I want you to do your best to name them before you proceed. So take a couple minutes, copy them down, try to name them, pause the video, come back in a couple. Welcome back. Now, let's start off here. So the very first molecule, this baby blue right here, if we look at it, we can see that we've got some hydroxyl groups, some OHs. Now, if we have hydroxyl groups, we need to remember that that would make it an alcohol. And whenever we're naming alcohols, we want to make the chain as long as possible that includes those substituents. And as I look, I've got 1, 2, 3, 4, 5. So since I have 5 alcohols, that makes it a pent. Now what is it? It's an alcohol. So pentanol. But if I look, I have 1, 2, 3 alls. So it's not a pentanol, it's a pentantriol. And where are my alcohols? My alcohols are on the 1, the 2, and the 3. So it'll be 1, 2, 3. Pentantriol or pentan 1, 2, 3 triol. So if you got that, dos claps, muy bien. B, pinky here. When we look at the pink molecule, we must look carefully and we see that we have an oxygen located in the middle of the chain. In other words, I've taken what was once an alcohol that's out by itself, and I've now turned the oxygen from having one bond with a carbon, i.e. being very primary or low sterically hindered, to one that is now bonded to 2 carbons, meaning I have a secondary situation, a little more steric hindrance, less reactive. And as soon as we go from having 1 carbon on the chain to 2, it is now an ether. And with ethers, we must remember we need to name each side for the substituents. So on one side I've got carbon 1, 2, 3, on the other I've got 1, 2, 3. Well, I'll be darned, I've got the same thing and they both have a fluoro on the 2. In other words, I have 2 things that are the same, so I need the prefix di. What do I have 2 of? I have two fluoros, and 1, 2, 3 would be a propyl. So the name for this ether would be di, because I have 2 of the same thing, di-2, because it's on the second carbon, di-2-fluoropropyl, 1, 2, 3, 1, 2, 3, ether. Next up, red. When we look at this red one, we see that we've changed how oxygen is bonded. We've changed the oxygen from being a primary situation, from the alcohol, to a secondary situation with the ether, to now the oxygen is out on the end, it's terminal. And the oxygen has changed how it's bonded. It's now double bonded. In other words, we've greatly increased the concentration of electrons in that region, so the polarity has gone up quite a bit. But the most important thing to notice besides that it is a carbonyl group, C, double bond O, is that it's terminal. And whenever we have a terminal carbonyl group, that makes it an aldehyde. And if I look, the first thing I want to do is I want to make sure that that alpha carbon there is included in the longest chain. And if I count, I go 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So it's definitely 6. Right here is the longest chain. And with 6 carbons, that would be a hexanal. Hexanal. And I don't need to include an address for where the carbonyl group is because for aldehydes, it must be terminal, it must be on the 1 carbon, but that does mandate my addresses now. So that's the 1 on the 2 carbon, what do I have? Very good. I have a methyl. So a 2-methyl, and on the 3, what do I have? Right here, I've got 2 carbons on the 3, which means that would be a 3-ethyl. E comes before M, so we put it all together, and the name for this molecule, according to the IUPAC naming system, would be 3-ethyl 2-methyl hexanal for the aldehyde. So if you're 3 for 3, why not give yourself 6 claps? 6 claps. Muy bien. 2 for each. Now we go to D, the beautiful purple molecule here. And we look at this beautiful purple molecule, we should zone in to this region right here. And that region right there is very similar to the aldehyde, except now my C double bond O, my carbonyl or carbonyl group, is now increased at steric hindrance. No longer is my alpha carbon bonded to 1 beta like it was in the aldehyde. It is now bonded to 2. Meaning steric hindrance is going up, reactivity has gone down, but this is still an extremely polar region. So what would we name this type of molecule? This classification is called a ketone. And ketones end in -one. Again, what do we do? First longest chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Doesn't really matter where we go, we get 7 regardless, so I'm going to go with these ones right here. Those are my 7. And if we have 7, we need to remember that the prefix for 7 carbons is hept. It's not a heptane because it's a ketone, it is a heptanone. Own for ketone. And now when we look at that, how do I get my ketone to be emphasized? I give it the smallest address possible. So if I come from here, 1, 2, 3, 4. If I come from here, 1, 2, 3, 4. So either way, it's on the 4. So it's a 4-heptanone. Now, when I looked at that, if I did 1, 2, 3, I've got a 3-ethyl. If I do 1, 2, I've got a 2-bromo. So obviously this gives me smaller numbers. 2-bromo, 3-ethyl, 5-ethyl. So I have a 3 and a 5-ethyl. That would be a 3, 5 diethyl. So the name for this, B comes before E. Remember the di doesn't matter in terms of alphabet. So the proper name for all of this molecule right here in the purple would be 2-bromo, 3,5-diethyl, 4-heptanone. Hopefully you're 4 for 4 and you've been doing your homework and you've been getting your practice and you're giving yourself an accurate self-evaluation. Next up, Hunter Green. Well, when we look at this guy, changes have occurred. I've taken my carbonyl, C double bond O, and I've added a hydroxyl group from an alcohol, and now I have a new classification of molecule. This is called a carboxyl group. Carbonyl and hydroxyl. Put those two words together and you get carboxyl or carboxylic group. And this carboxylic group makes this an acid. So this is a carboxylic acid. And notice we have benzene here. When you have benzene, a part of a carboxylic acid, remember from yesterday's lesson that this is called benzoic acid. So benzoic acid, and if I look, here's the most important part of the benzene ring, makes it the carboxylic acid. So it'll be a 1, a 2, and a 3. 1, 2, 3. Since I have 3 of the same things, the prefix would be tri. And they're all chlorines, and that would be trichloro. So 1, 2, 3, trichlorobenzoic acid. Now, one thing that's important to remember from class the other day is why is this an acid? Well, first off, it's an acid because of this hydrogen right here. And the way, remember, that I think about that hydrogen is I think about going into a very dark cave. If you're in a very dark cave, an area that's very electronegative from those oxygens is going to have a lot of electrons around it. And those electrons around it are going to make this region right here that I've outlined. Right here, looks kind of like an L. I haven't included the proton, but I've included the oxygens. It's going to make that region very negative. Well, if I was in a dark cave, let's pretend that darkness is the negative region. Now, no matter how small that flicker of light would be, that opposite of darkness, that opposite of negative, this proton, no matter how small that proton is in that area of darkness, it's going to stick out. So that's what makes it an acid. The polarity that results and the positivity of this proton make it so that it can be released. Now, why is it a weak acid? That was the question I left you with on Wednesday. It's a weak acid because if this is positively charged and all of this is negatively charged, it'd be pretty hard for that proton to leave. So it would have to be just the right circumstances. Hence, these are weak, and also because of that positive charge and all of that negativity, they're acids. So those are why we got carboxylic acids, a little bit of chemistry there for you. Now, last but not least, we have F. The molecule in F is not a carboxylic acid, but it certainly has a region that looks very carboxylic. Right here, I've got a carbonyl group, and adjacent to it is an oxygen. Remember, esters are the product of an acid-base reaction. In the acid-base reaction, that would produce this ester would be two things. If I look at this region right here, notice that region looks very carboxylic acid-y. This would have been the carboxylic acid that would be used to produce this ester. And then over here, I've got another component of the acid-base reaction, that ethyl group. And that would be the result of this alcohol. So esters are produced when we take carboxylic acids, which are acids, and combine them with alcohols. And when we look at that alcohol, we see an OH group. And if you remember, NaOH, all of our bases, KOH, the bases that you use in organic chemistry contain a hydroxyl group. And that hydroxyl group is what makes them basic. This acid, we differentiated why this hydroxyl group is acidic, whereas this hydroxyl group is missing that C double bond O, that adjacent carbonyl group that is making this proton stick out more, that is making this proton more acidic in nature. Over here with an alcohol, without that, it's going to behave as a base. Well, if I look at that, I can see that I've taken my pink line, and it's existing right there, and I've got my carboxyl group here. And so if I were to name this alcohol, this is ethanol. 2 carbons, ethanol. Over here, what would this carboxylic acid be? 1, 2, 3, 4, that's a bute. Very good, Miss Monty. Butanoic acid. Well, whenever we make an ester, the ester's name actually tells you exactly what it was produced from. And the first word we always use is the name from the alcohol that would have been used to derive it. And that alcohol can be found here. So we're always going to name that first, and that would be an eth. It's a substituent of the ester, so it is called an ethyl. And then when we look at the longer component, the butanoic acid, well, it's no longer carboxylic acid. It is now an ester. It's going to have a different suffix. So it's not going to be ethyl butanoic acid because this is not an acid anymore, it's an ester. This is ethyl butan O8. Esters in the word O8. And so whenever you look at the name for an ester, you know what produced it, ethanol and butanoic acid. So that's how we name esters. Well, let's pick up in our notes with the next component that we want to discuss. And the next component we want to discuss is going to start, let's start with number 28 in the notes. I'm just making a prediction. This is Wednesday, so Thursday, tomorrow, or yesterday, if you're watching this video on Friday like you're supposed to. On Thursday, I'm hoping that Mr. B got through 27 in the notes, naming carboxylic acids. If we did not, please go through the notes and fill in the remaining information. But we did go through how to name carboxylic acids. We did go how to name esters up here, so hopefully most of that was review. If not, I hope you paid attention. But let's go through naming esters, and then I want to get through, let's say, 36. Let's just finish up the notes here. So 28 in the notes says naming esters. The name of an ester, of course, I just pointed out, comes from 2 words. And those 2 words are taken from the name of the alcohol and the acid that produced it. B, the first word indicates the alkyl component of the alcohol. Alkyl, in other words, the carbon chain component. The alcohol that's left over when the hydroxyl group left. And the second word is the carboxylate, the C double bond O adjacent to it. Name of the carboxylic acid. So in A, it says draw or name the following. So in A, I believe I gave you the name pentyl ethanoate. Pentyl ethanoate. And when we look at this, remember what I just told you from reviewing how to name the brown molecule there. Whenever we're naming esters, we've got 2 components. We've got the first component. This tells me all about the alcohol that made it. Ethanoate, this tells me all about the carboxylic acid that made it. And so when we look at that, pentyl, that would have come from pentanol. 1, 2, 3, 4, 5, OH. That is pentanol. The ethanoate, that's going to come from ethanoic acid. There's my carboxylic acid with 2 carbons, ethanoic acid. So this is pentanol plus ethanoic acid is going to produce this ester. So let's show what happens. Well, remember this is an acid. Acids donate protons. So that proton will get pulled off, and we'll learn about that later on in this unit, or not unit, later on in this class. We'll go through the chemistry in a little more detail. And bases, remember, donate hydroxyl groups. Well, if you remember from acid-base reactions, a byproduct of acid-base reactions is often the combination of H and OH. Well, when I combine H and OH, I have water. Water is a common byproduct of acid-base reactions. Well, when that happens, what's going to be left behind? Well, if this proton left, it's not going to take any electrons with it. It's not going to take any electrons with it because foundational rule, electronegativity, says oxygen is more electronegative. And if oxygen is more electronegative, it's going to take those electrons that were in that oxygen-hydrogen bond in that hydroxyl group, and it's going to then become negative. Well, over here, I've got an OH group that left. Well, if that oxygen and that hydrogen leave this carbon chain, who's taking the electrons in this bond? Well, we should ask ourselves, who's more electronegative? The carbon on this side of the bond or the oxygen on that side of the bond? And we know from chapter 1 that oxygen is more electronegative. So oxygen here is going to take both of those electrons in that bond, please, and notice it's going to become negative. Well, what happens when a negative comes into contact with a positive? Another foundational rule takes over, and we know opposites attract. Well, if hydroxide took the negative, that's going to leave behind a positively charged carbon. Well, I got a positively charged carbon here. I've got a negatively charged oxygen there. The result from those bonds cleaving as the OH and the H talk to each other, the acid and the base talk to each other, and that's how we make an ester. So a byproduct of esterification is water. And now when we put it all together, we would have pentyl ethanoate. 1, 2, 3, 4, 5. There's my 5 carbons. And those 5 carbons are going to bond to my ethanoate. There's my O right there. 1, 2. Notice here, there's my ethyl. Notice here, there's my pentyl. And we put it together, we get pentyl ethanoate. So I went through a lot of detail there in how esters are produced. Now let's do another one. Let's do one without all the chemistry detail, but you're free to pause the video and add all that chemistry detail if you really want to search yourself and engage the old noggin. But in B, we've got the name octyl ethanoate. Octyl ethanoate. So octyl ethanoate. Well, octyl ethanoate is going to be produced from ethanoic acid and octanol. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Octyl. 1, 2. Ethyl. So now I've got here, remember this is pentyl ethanoate. To make it octyl, 1, 2, 3, 4, 5, 6, 7, 8. So now it is octyl from the alcohol, octyl ethanoate. Now when we look at our next structures are as follows. In C and D, you start with the picture and you have to come up with the name. Let's change the colors here. We'll use some pink and some blue. Boys and girls. And so when we look at picture C, that wasn't very good. We've essentially got that, I believe. Let me double check. 1, 2, 3, 4, and 1, 2. 1, 2, 3, 4 carbons, and 1, 2. So now when we name this, we look at it, and on this side, this would be the alcohol. That would be an ethyl. And over here, 1, 2, 3, 4, that's a bute. Butane O8. So we have ethyl butanoate. Now what would this be produced from? This would be produced from ethanol and butanoic acid. Butanoic acid would donate a proton to the ethanol. The OH group, the hydroxyl group from the alcohol, would leave with that proton, making water, and then the opposites would attract. producing this ester. So that is ethyl butanoate. And now our next one, let's look at it. I've got 1, 2, 3, 4. 1, 2, 3, 4. Double bond O, down to an O, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So what did I change? Well, notice I didn't change my butanoate at all. My but, 1, 2, 3, 4. I still started with butanoic acid. But instead of having an ethyl, I have 1, 2, 3, 4, 5. So it is not an ethyl. 5 is a pent. It's a pentyl butanoate. Now, what I find fascinating about esters is a lot of people think our eyeballs are the most precise measuring device because, in all honesty, they're differentiating nanometers from nanometers. A couple hundred nanometers, and our eyeballs are able to see red, orange, yellow, green, blue, indigo, violet, and every shade in between, which is fascinating. But what we often overlook is our sniffers. The old sniffer. Well, if you look at 29, pentyl ethanoate, A, that smells like banana. When we go from pentyl ethanoate to octyl ethanoate, in other words, we're just changing it by 3 carbons. Our nose is able to differentiate these, and that's fascinating. We're going from banana to orange. And then we had our butes, right? We had our ethyl butanoate, that smells like pineapple. And then we just had 3 more carbons. We go from an ethyl to a pentyl butanoate. And that smells like apricot. And those are completely different stenches. And our nose is able to differentiate those. And our nose says, those smell nice. Those smell amazing. And as we understand these things, I think in my mind, it points to the precision of our creation, which is pretty interesting because I believe that we were precisely and carefully and wonderfully made. Now next up, so that's how we named esters. Let's pick up with 30. So as we've gone through this unit, we've discussed lots of compounds that contain a new element, the number 2 most electronegative element, oxygen, which is very important. And by adding oxygen to the situation, our carbon chains get quite exotic and quite interesting because we now have a high concentration of electron density around that oxygen due to its electronegativity. We have alcohols. Then we put them in the middle of the chain. Now we have ethers. Then we take that oxygen instead of single bonded, we double bonded, aldehydes on the end. Now we increase the steric energy to move that carbonyl group into the middle chain. Now we have ketones. Then we took our aldehyde and we combined it with our alcohol and we made carboxylic acids. Then we took our carboxylic acid and we combined it with our alcohol and we made these amazing things called esters that have these amazing aromas. But we have one really important element. It's the most abundant element in our atmosphere, nitrogen. And when we bring nitrogen to the table, we have 2 new classifications, amines and amides. And so let's discuss amines. Amines are a lot like ethers. Amines are a lot like ethers. Now, if you remember, Wyatt brought up something very interesting, a very cool thought about ethers I'd never thought of. And whenever we have an ether, oxygen is the chain. It is the foundation. It is what everything is coming off of. In amines, it's not oxygen, it's nitrogen. So 30. In amines, the central atom is a nitrogen atom. Amines are derivatives of ammonia. Ammonia is NH3, the simplest organic molecule that contains nitrogen. Remember that the geometry of ammonia is going to be pyramidal, and that lone pair up top, very important. If we look at this molecule up top, it's negative because nitrogen in its electronegativity is going to hoard those electrons. And below it, we've got a bunch of protons. And so is this molecule going to be quite polar? Elena? Yes! Very good, Elena. It will be quite polar. Negatives and positives. And is that going to cause it to be reactive? Absolutely. Now this is ammonia. Now how do I make it more of an organic situation? Make it more organic than just the fact that it's made up of non-metals. I would want to bring in carbon. And as soon as I bring in a carbon, and I replace one of the hydrogens with a carbon, now I have, so if I take that off and I replace it with a CH3, now I have an organic substance called an amine. A-M-I-N-E. And so if you look at A, B, and C, I've got some names for you. And I bet you can come up with them. Don't just copy them down really quick, but take a pause, look in your notes, and look at 30A. It says methylamine. B says dimethylamine. And C says trimethylamine. Notice these are named a lot like esters. We've got all the substituents, put in alphabetical order in front, followed by the word amine. Just like with esters, we had all the substituents, put in alphabetical order in front, followed by the word ester. Very similar. So methylamine. There's methylamine. Why do I only have 2 hydrogens here? Well, look up here. What did I have to remove from ammonia, NH3, to add a carbon? I had to remove a hydrogen. So that is methylamine. Next up is dimethylamine. Well, if I wanted to make dimethyl, I would need to have 2 CH3 groups, or 2 methyls. Now notice dimethylamine. Dimethylamine. And then the last one I had for you was trimethylamine. So now I must remove that last hydrogen. And now I have trimethylamine with my lone pair. And it would still be pyramidal, and it would still be polar. But with those carbons comes fluff. With that fluff comes shrubbiness. With that shrubbiness comes steric hindrance. And the nitrogen is now less able to be interacted with. 31, in an amide, A-M-I-D-E. So amines are a lot like esters. Amides are similar but different. We would know they're similar because they both start with the word A-M-I. The letters A-M-I, not the word A-M-I. But instead of saying A-M-I-N-E, we say A-M-I-D-E, amides. In an amide, 31, the hydroxyl group, OH, of a carboxylic acid, COOH, the carboxyl group, the hydroxyl group OH of a carboxyl group, COOH, is replaced by a nitrogen group, NH2. So in A, I've got the word methanamide. So when we've got amides, what are we essentially doing? So we've got amines, which were a lot like, very similar to esters. Amines, we've got nitrogen as the central atom. Esters, we've got oxygen as the central atom. So this would be dimethylamine. This would be dimethyl ether. Sorry, not ester. Crazy Mr. B. Ether. Dimethylamine, dimethyl ether. But now with an amide, what's changed? So in an amide, as opposed to a carboxylic acid. With a carboxylic acid, we've got a carbonyl group, and adjacent to that carbonyl group is a hydroxyl group. So this would be ethanoic acid. But with an amide, what am I doing? I'm changing that OH group into a nitrogen group. So it would behave similarly. Here, I've got ethylamide. Ethanoic acid, ethylamide. So if you look in 31, the first word I've got for you to try to draw is methanamide. 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 Methane, 1 carbon. Well, there's my carbon right there at the bottom of that double bond. And amide, meaning I better have an NH2 group. So that is methanamide. Next up I've got is ethanamide. Ethanamide. I'm going to call that ethylamide. I meant ethanamide, sorry. This is ethanamide. Ethan, 2 carbons, 1, 2, 1, 2, ethanamide. And what makes it an amide is that group, CONH2, or NH. And then the last one I've got is benzanamide. Benzanamide. Notice here I've got benz, which means I've probably got a benzene ring. Now how do I make this benzene ring an amide? Well, remember we had benzenoic acid. That's benzenoic acid. Now how to make it benzenamide or benzamide? I replace the hydroxyl group with an NH group. In 32, well, as we saw earlier, esters were the product of carboxylic acids and alcohols. Amides are similar. Amides are derivatives of carboxylic acids and ammonia, or an amine. A byproduct of these acid-base reactions is going to be very similar to the byproduct of the acid-base reaction involving carboxylic acids and alcohols. So water molecule and an amide are going to be produced from this. This is much like the production of esters. So below I've got two things I'm adding together. I say I've got propanoic acid plus ammonia, and I'm going to make propanamide and water. So let's see if we can draw that all out. Propanoic acid. Prop means 3 carbons. Oic acid means I've got on the terminal end of that prop, 1, 2, 3, I've got a carboxyl group, a C double bond O, OH. So this is propanoic acid. And to it I am adding ammonia, NH3. And what's going to happen is I'm going to pronate, and my alcohol group is going to leave, and I'm going to produce 2 byproducts. My H is going to be adiosed. My hydroxyl group is going to be adiosed. And these 2 things are going to combine to form HOH, or water. And as soon as that happens, I'm going to have an opposites attract situation here, and I'm going to make propanamide. Propanamide. 33, naming amines, pretty simple. Amines, remember, are nitrogen as a central atom, very similar to ethers. In the common name, the alkyl groups bonded to the nitrogen are listed in alphabetical order. In other words, name all the substituents, put them in alphabetical order. The suffix amine is put at the end. Now, one thing that's important to know is aromatic amines have a special name. Aromatic, remember from last chapter, aromatic means benzene. And a benzene ring that has an NH2 group attached to it. There's a benzene ring. There's an NH2 group attached to it. So notice this is an amine because I have carbons coming off of a central nitrogen. It doesn't look so central. But this has a common name called aniline. 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 Or maybe it's aniline. I don't know. From South Central Indiana. I'm sorry, Faith. Calm down. Anilines. So that would be aniline. So in 34A, aniline, nice and easy. Bada bing, bada boom. There it is in green. B says ethyl methyl propylamine. Ethyl methyl propylamine. So here's the amine part. Let's do an ethyl. Ethyl, eth, 2 carbons. Ethyl methyl. Methyl means 1 carbon. Ethyl methyl propyl. Prop means 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Ethyl methyl propylamine. So these are pretty simple. C. If we look, I've got an aniline, don't I, or an aniline. So I have one of those in C, but on top, or drawn on this, I've got 2 bromines. 2 bromines. Well, if I have 2 bromines on an aniline, I should have that aniline as the very end. It's an aniline. And if I have 2 bromos, this would be the 1 carbon. 1, 2, 3, 5. 3, 5, di-bromo-aniline. And then lastly in D, I've got a nitrogen group off on the end, an NH2. And on that NH2 group, I've got 1, 2, 3, 4, 5. And then an NH2 after that line. Well, I've got 1 carbon here. 1, 2, 3, 4. Yes, I have a line, but on the end of that line is an NH2, so I only have 4 carbons. 1, 2, 3, 4. That'd be butylamine. A-M-I-N-E. Butylamine. 35, naming amides. Amides are named by dropping the ic acid component or oic acid component of the carboxylic acid name, the derivative, the component that an amide came from, and you're going to replace it with the suffix amide. So first we have this ethanamide. Ethanamide. There's the eth. There's ethanoic acid. The difference between a carboxylic acid and an amide is the fact that this hydroxyl group is replaced with an NH2 group, and it is now ethanamide. Notice I got rid of the oic acid part and replaced with amide. Ethanamide. Next up I have butanamide. Butanamide, bute, 4. 1, 2, 3, 4. Now I have butanamide. And next up, if I look at C, notice I have 1, 2, 3 carbons. 1, 2, 3 carbons. I have a double bonded oxygen. I have an NH2 group all on the terminal end. Prop. 1, 2, 3. Propanoic acid would have been what I started with, and to turn that into an amide, I reacted with ammonia, NH3, and I now have propanamide. Propanamide. And lastly with D, I have 1, 2, 3, 4, 5 carbons in the longest chain. 1, 2, 3, 4, 5 carbons in the longest chain. And when I look at that, I also have, after 1, 2, 3, 1, 2, 3, I have a methyl group. So if I have a methyl on the 3, wouldn't that be a 3 methyl? And if I have 1, 2, 3, 4, 5, wouldn't that be a pentan? And since I have an NH true, pentanamide. Very good, students. Thank you so much for paying attention. Here's what I want you to do now that you've watched the video. I want you to take a picture of some of the notes you took while we were going through this. I'd also encourage you to maybe write some of those notes on your last sheet, your unit reflection sheet. But please take a picture of those and email me a copy of those notes prior to class on Monday. That'll be good evidence that you have watched the video. My email is paul.blmenberg@lhsparker.org. Thank you. I miss you. Have a happy Friday. Adios.